This video is about energy calculations. You'll remember all the way back to year 7 talking about things like potential and kinetic energy, and maybe about work, that's the energy you use when you move a force. But this year we have to be able to do calculations to actually work out numbers for these types of energy in joules. And then quite hard, we have to be able to do some calculations involving conversions of energy. So you have to remember the stuff from core physics about the conservation of energy. If you've got one kind of energy, it's going to always turn into a different sort. You can't destroy energy. It's always going to go somewhere. Just to get you thinking about these kinds of energy, this little animation's got a skateboarder on a track. Over here we've got a graph. We've got the different kinds of energy we might have. So we've got the kinetic energy, we've got potential energy, and we've got the total energy. We'll talk about thermal in a minute. So the kinetic energy has got to do with how fast he's moving. So at the moment he's not moving, so his kinetic energy is 0. His potential energy is to do with how high he is. So he's lifted up high. I can lift him even higher, give him some more potential energy. And his total energy, obviously we've only got potential energy, so his total energy and his potential energy is the same. If I let him go, see that as he falls, the energy turns from potential energy at the top to being all kinetic energy at the bottom, back into potential, kinetic, potential, and so on and so on. But the total energy of the system remains the same. Okay, it's just a conversion between those two forms of energy. Okay, so hopefully you can see that that's not very realistic. If you've ever been on a skateboard, you'll know you can't just go up and down the ramp all day. Why is that true? Well, it's true because of friction. So at the moment you can see down here I've got the ability to change friction on this ramp. That was with no friction. Here we've got some friction, so if we allow for friction and we start him off again, okay, then you'll see that we're still converting between potential and kinetic energy, but every time he goes a little bit less far up the ramp, and that's because as he moves, the energy of friction is producing heat. So slowly all of the energy is turning into heat. More and more of the total energy is in the form of heat energy, and eventually if you leave him long enough he's going to stop in the bottom. So just to summarise that, at the top of the slope, when he's up here, he's just got potential energy. As he goes down the slope, that turns into kinetic energy. But if there's a force of friction, then some of the energy turns into heat, and the energy used in moving against friction has got this rather strange name, this scary word, work. Okay, so that's got us the basic ideas about energy, but now we have to be able to do that second bullet point. We have to be able to actually calculate energy. So the energy you use when you move a force, the work, is simply just the force times the distance you move. Work equals force times distance. Remember, this equation will be on the formula sheet for you. You haven't got to learn it. You just need to understand what the things mean. So if the skater moves 20 metres against a 30 Newton frictional force, how much work is done against friction? Simply all you have to do is work equals force times distance, 30 newtons times 20 metres, 600 joules. As ever, just be careful with the units. If they had that in centimetres or kilonewtons, then you'd have to allow for that. Okay, the second one is potential energy. Well, the potential energy really is just the work we do against gravity, and the work against gravity depends on the force you need to lift something, with its mass times its gravity, that's its weight, times the distance you move it, that's its height. So that equation becomes the potential energy is mass times gravity times height. So if we've got a 60 kilogram skater and he's at the top of a 10 metre drop and he's on the Earth, crucially, because this would be different on different planets, but normally we assume we're on Earth, we round gravity off a little bit on Earth to be 10 just to make the numbers a bit easier. So his potential energy is mass times gravity times height, 60 kilograms, 10 metres high on Earth, gravity is 10, and therefore 6,000 joules. Okay, the trickiest equation is the kinetic energy. Kinetic energy, EK, is a half times the mass times the velocity squared. Be careful when you put this in a calculator, only the velocity part is squared, so don't do a half times the mass times the velocity and then press squared and get everything squared, just the velocity is squared. So for example, the kinetic energy of a 60 kilogram skater moving at 10 meters per second is a half times 60 times 10 squared. Stick that in your calculator carefully, you'll find it's 3,000 joules. Okay, so we've done some calculations with the different sorts of energy. There's a bit more practice on this slide. If you're not feeling too confident with those and you want to have a go, let me just show you these ones. So pause the video there if you want to and have a go at those calculations. I'll just put the answers up for you in a sec. Okay, and once we can do these calculations, then we can start to look at actually using these numbers to work out and predict what will happen. So this is why it's really useful. If, for example, you throw a tennis ball of mass 0.2 kilograms up in the air and it's going at 20 meters per second and you want to know how high it'll go, you can actually work that out by using the conservation of energy. So the first step is to work out its kinetic energy at the start. Well, we know the kinetic energy formula, half mv squared. So we have to do a half times the mass times the velocity squared is a half times 0.2 times 20 squared. That comes to 40 joules. Okay, this is the kind of trick question that confuses people. When it gets to the top, what's its kinetic energy going to be? Well, don't start writing down a half mv squared. Think about it. At the top, it stops. If it stops, the kinetic energy is just 0 joules. You can do a half times 0.2 times 0 if you like, but that will be 0 joules. So where's the energy gone? Well, the energies must have turned into potential energy. Okay, so we've now got gravitational potential energy instead. This lets us work out how high the ball's gone, okay, because we know that potential energy is mgh, and we know crucially that that's got to be 40 joules when it gets to the top. That's at 0.2 times gravity on Earth is 10 times the height. If you work that out, 0.2 times 10 is 2, so we get 40 equals 2h. It will go 20 meters in the air. That's a fairly straightforward calculation. Just be careful at this step that if you try to work out the potential energy at the top, you're not doing mgh straight away. You've got to notice it's the same as the kinetic energy was at the bottom. Okay, this is another slightly harder calculation, same sort of idea. So if you've ever been on Apocalypse at Drayton Manor, it's approximately 50 meters high. Let's say there's 500 kilograms in the system dropping, and we're trying to work out how fast it's going to hit the ground if the brakes fail. And then a tricky extension to this, suppose it's not just dropping freely, there's some friction on the track. Could we work that one out? So first step is work out the potential energy at the top. Potential energy at the top is m times g times h. That comes to 250,000 joules. So what's the kinetic energy going to be at the bottom? Hopefully you can see we're not going to write half mv squared. We're just going to write that Ek, the kinetic energy at the bottom, is going to be the same as Ep, the potential energy was at the top. This is a little bit trickier with the algebra. We've got a half mv squared there equals 250,000. Okay, half times the mass was 500, so half times the mass is 250. So 250 v squared equals 250,000. Divide by the 250, we get v squared equals 1,000. Do the square root of 1,000. We hit the bottom at 31.6 meters per second. Okay, allowing for friction on the track. Suppose actually when you fall, you don't just fall freely, there's some friction, so some of that energy is turning into heat on the way down. Okay, well we've still got 250,000 joules of potential energy at the top, but now we've done some work against friction on the way down. How big is that? Well, that's force times distance. I've written that the wrong way around really, but there's the force 1,000, there's the distance 50. So we've lost 50,000 joules on the way down. Okay, so we had 250,000 joules of potential energy, 50,000 turned into work. So the kinetic energy at the bottom is not going to be 250,000 anymore, it's only going to be 200,000. Okay, so then it's the same calculation as above. 250 v squared, that's a half mv squared, is now only 200,000. V squared is 800, that's 200,000 divided by 250, gives you a velocity at the bottom of 28.3. Okay, so just to remind ourselves, the key thing is to understand what these three kinds of energy mean, then to be able to calculate them with the equations. They'll give you the equations, so don't waste your time learning those, just make sure you understand them. And then the hard sort of calculations are actually applying those using the principle of conservation of energy.